Again. So today I'm going to change tacks and talk about a very recent modeling project on modeling the biomass of nearly pristine, which means natural coral reefs, and then use the model to study the effect of fishing. And this is work done with Wendy Morrison, who's an extremely smart graduate student in biology, who I'm co-advising. Her advisor is her other advisor is quite a distinguished aquatic ecologist. Abi Cinch is my graduate student, actually in physics, who just graduated, and he's doing a postdoc in neuroscience at the University of Munich. Hao Wang was my postdoc, who's now an assistant professor at the University of Alberta, and myself. Before I do that, and I apologize for this slide, I'm just learning PowerPoint, and I couldn't remove the picture on the right. But this is for the students here. So I strongly believe that the combination of biology and dynamical systems is both extremely interesting and really one of the growth areas, not just in mathematics, but in science in the coming years. So I list some topics, some I mentioned, some I didn't mention, which I think are the most exciting research areas in the sort of intersection. And I can probably give you 100 problems, literally, in an hour. Very interesting problems related to these things. I have so many interesting problems, and certainly not nearly enough students or postdocs to work on them. So certainly infectious disease modeling, or more generally population modeling with more realistic mixing assumptions. So you're going to see an example of that today, because our model is going to have a refuge. Adding more realistic immunology to the transmission models. So a quiz, actually this is really maybe an exam question. Where is the immunology hidden in the SIR model? So I stress that in that model, everybody has the same immunology, but what is it? I'm sorry? Exactly. Both coefficients. The transmission coefficient and the removal rate. So the little bit of common immunology is indirectly, well, is hidden, in a sense, in those two parameters. Much more is known about immunology. So to add more realistic immunology to the models. Immunology is an extremely interesting subject, but if you pick up many textbooks, it's extremely intimidating. But I give a reference to some books in the book, including a great book on immunology. I call it Immunology for Idiots. But you can just read it, not quite as a novel, but you could read it with knowing no biology, and it gives you a lot of insight, understanding into immunology. Spatial models of the spread of infectious disease, maybe starting with network models, which are something in between ODEs and PDEs, but certainly also PDE models for transmission models. The problem there is data. I mean, it's kind of hard enough to get number of infectives in a city every week. If you want to parameterize a spatial model, you need the number of infectives per neighborhood. In the United States, we call it zip code, per neighborhood or something like that. You need much more fine data, which usually doesn't exist for infectious diseases. In-host and between-host models. So, well, first of all, the individuals are implicit in these models, and also they have the same immune system. So add individuals interacting with other individuals, so think maybe a network, and then think that each person has a different immune system. Devise better models of evolution of infectious diseases. So I don't think it's difficult to write down a reasonable model for the spread of, say, flu over the short term, but not over the medium term or the long term, because flu evolves very quickly. So what one needs to do and this is really a big challenge. This is a very big challenge. I know the guy at the CDC, or at least he was at the CDC, who is more or less in charge of choosing the cocktail for the flu shot, at least that we get in North America every year, and it's more or less a guess. I mean, he's desperate to use mathematics, absolutely desperate to use mathematics to make it less of a guess. So you want to add evolution, so this is, of course, on the genomic level, to transmission models, sort of couple them. One of my dreams, although I haven't talked very much about this, is, well, I mentioned very briefly, that if you want very precise models, you need so-called agent-based models with individuals acting with other individuals. They seem very, very different than like ODE or PDE models. But I think at least for many classes, they're maybe not so different, and somehow they can be unified. So the agent-based model is so-called bottom-up modeling. The ODE, PDE, dynamical system model is top-down, and I think there's ways of unifying the two. And then finally, something which I started working on in the spring, again, with biologists who are doing experiments, and those are mathematical models of biofilms. So a biofilm you think of as a bacteria colony, maybe a couple of different species, maybe not, on a surface, like a petri dish. So if you have bacteria like in a liquid, that's more or less well mixed. So you can write down ODEs. But if you have bacteria growing on a petri dish, then that's not well mixed. And there are lots of questions, lots and lots and lots of questions about how they grow. It's amazing how little is known about how bacteria grow in a petri dish. And this is, of course, related to more realistic mixing assumptions. It's also related to, there are many, there are certainly some, say, bacterial infections, like in bones and so on, in the heart, which are very hard to treat. And it's thought that the reason that they're hard to treat has to do with biofilms. So there are many applications of this. So any students who are interested in pursuing any of these, just let me know. Be happy to talk with you about that. Okay. So usually I don't talk about personal things during talks, but this picture was taken during Christmas at my wife's parents' house last year. That's a joke. Well, your mother-in-law's must be worse than mine. This picture is, I present this for two reasons. So I'm a much better mathematician than I am photographer. So this was taken with my camera, my phone camera a few months ago. This is Abby, that's Wendy, that's Hal in the lab. They're doing some refuge experiments which were motivated by what I'm going to talk about. And this is how the picture came out. Unfortunately, he's in Germany, he's in Canada. So the three of us probably aren't going to be reunited for a while. If anyone knows how to unblur this, please let me know, because I don't know how to do that. Okay, so this is a picture taken at Kingman Reef, and I'll show you on a map where it is. It's thought to be a pristine, meaning natural coral reef, as untouched by humans as possible. Now, of course, this isn't the usual picture you see in advertisements for, traveling to coral reefs, like in, along the Yucatan or in Australia, right? I mean, this is obviously, if they use this as, the advertisement, I'm not sure many people would go there. This is a stable picture. Okay, so this isn't sort of a transient. This is stable. So if you went back there a few hours later, a few days later, or a few months later, you would see more or less this picture. Okay. Okay, so some background. So coral reefs are called the rainforests of the ocean, right? They support a huge amount of biodiversity. According to the government agency in the United States that deals with such things, only about 30% of the world's coral reefs are healthy, and 20% have already been destroyed. Coral reefs are under threat, it's believed, from overfishing, global warming, rising acidity of the ocean waters, pollution, oceanfront development, and so on. Many scientists believe that all these things are bad, but they can't prove it. There's sort of no proof that these things are bad. And that's one of the motivations for our model, is to study these things using our model. And in particular, we're concentrating so far on overfishing. And the short answer is we show that overfishing is bad. Very clearly bad. Okay, so there's significant interest in trying to stabilize or restore damaged coral reefs. So according to my colleague at Georgia Tech, who's actually one of the world's experts on trying to restore damaged reefs, if we just wait, it's going to take at best tens of thousands of years for many of these reefs to restore themselves. So he thinks it's a very good idea to try to actively restore the reefs. And it seems that many of these experts believe that the first step in trying to restore a damaged reef or a damaged ecosystem is to understand the functioning of the ecosystem, in this case the reef, in the natural or the pristine state.
How do you know the coral will be restored? Because you didn't remove actually the cause of the damage. So how do you know?
Well, because let's suppose that there are studies that show that corals are very sensitive to temperature change. Okay? Eventually, we have global warming. Eventually, we're going to have another ice age. Now, there have been recent so-called high-profile field studies of several northern line island reefs. I'll show you that on the next slide. But this made all the big newspapers in the United States. It was the cover of National Geographic magazine and so on. And the study included several reefs, including Kingman and Palmyra reefs, which are believed by the experts, although again they don't know this, but it's believed to be a baseline for the natural state of coral reefs. That's why they're so interested in this. So this is a map. This is the equator. I don't know. This is Samosa. This is Cook Islands. This is French Polynesia, Tonga, Fiji, Marshall Islands. There was action here in World War II, but it's pretty isolated. This is Kingman Reef. So it's about 1,000 miles south of the Hawaiian Islands. This was the first paper that I saw. This is a field study. It's a little bit more than a year old. It was published in PLOS One. I first read about this in Science, not last Christmas, but the Christmas before. And I was reading it at night, and it literally had me up all night, wondering how could this possibly be? Okay. So again, this is the reef, and the question is, what's odd, what's strange about this reef? And of course, you don't see little fish. You see big predators. In this picture, you see reef sharks. In the previous picture, you saw reef sharks. You saw groupers, snappers, red snappers. But here, no little fish. Where are they? And how can these big guys survive without eating little fish? Okay, so this is Kingman Reef. This is actually a reef not so far away from Kingman, but it's around islands with a fair number of people who fish, almost commercially fish. So this is a pretty fished reef. So you think about this as being almost a conventional reef. So this is the reef of sort of the travel brochures. So what are the differences? Well, the most amazing difference is that at Kingman Reef, 85% of the fish biomass, so you think total weight of the fish, is in predators, top predators. Again, reef sharks, mostly reef sharks, snappers, and groupers. Okay, so this is what's called an inverted biomass pyramid, that you have many more, much more biomass on the top of the pyramid than you do at the bottom of the pyramid. And I'll show you some pictures in a minute. This doesn't seem possible. It probably seems like at first it seemed like it violated the first law of thermodynamics. But there's also something, it doesn't. There's something called an energy pyramid. It does violate an energy pyramid, but it doesn't violate a biomass pyramid. So this is an example of an inverted biomass pyramid. Also, although people here can't tell, these corals are very healthy. They're extremely healthy. These are not. Now, part of it is, of course, the difference in the picture, but as far as things you can see, like the types of bacteria, the amounts of bacteria, and so on, this is much healthier than this. And finally, this reef essentially is unfished. Well, is unfished. But this reef is somewhat heavily fished. Okay, so where are the prey? They're hiding. They're hiding in the coral. They use the coral as a refuge. Okay, so any such, so we talked about weak mixing, we talked about homogeneous mixing or mass action, right? Mixing when we talked about epidemic models, about, mixing, mass action mixing of susceptibles and infectives. That means they're sort of intermingled. Obviously, this is as far from that type of case as possible, right? This is almost the other extreme. Okay, so this is almost a silly example of a normal biomass pyramid in the ocean. So there's no way I would show this during a biology talk, but you have the phytoplankton, you have zooplankton, which eat the phytoplankton, but you have much less biomass of zooplankton than you do phytoplankton. Then you have herrings that eat the zooplankton, and then you have less cod that eat the herrings, and then you have shark that eats the cod. So this is like a normal, this is a sort of a normal biomass pyramid. Okay, so for a normal pyramid, you have the prey down here, and you have levels of prey, and then you have the predators up here. For an inverted biomass pyramid, you have the prey on the bottom and the predators on the top. So I like this paragraph about a normal biomass pyramid. So 300 trout are needed to support one man for a year. The trout must consume 90,000 frogs that must consume 27 million grasshoppers that live off 100,000 tons of grass. Okay, so stable inverted biomass pyramids seem to be a signature of pristine coral reefs. Again, they don't know this, but the experts, including my colleague who's an expert, believes this. They don't know why. And actually, our modeling hopefully gives some insight about why. As you might imagine, inverted biomass pyramids, when I say inverted biomass pyramids, I mean stable inverted biomass pyramids. They're extremely rare in ecology. The only documented example is in the ocean, actually in lakes too, with phytoplankton and zooplankton. And this is actually so well known, it's in ecology books. My Georgia Tech colleague has done a lot of diving off of a reef, not a coral reef, but a reef off the North Carolina coast. And he believes, although he hasn't done measurements, but he believes that there's a stable inverted biomass pyramid there. And the reason there is that it's not a closed system. Lots of prey fish keep coming in. So that's, in a sense, cheating. Okay, Odom, who's one of the most famous ecologists, who wrote probably the best-selling introductory text on ecology, hypothesized that the inverted biomass pyramid for the phytoplankton is due to the very high turnover rate of the phytoplankton. And then others joined in, so other hypotheses are the low turnover rate of predators and the influx of essentially food. But nobody knows. Nobody knows. And as I'm going to show you, in this case, it's embarrassing that they didn't know, because they knew how to construct a mathematical model, these guys, because it's a model actually in his book to be able to show this. So in a recent paper, which actually already appeared a few months ago in the journal Ecological Modeling, this is what in biology is called a theoretical paper, because there's no data. But we find 3 mechanisms. So we exhibit 3 different types of models, each with a different mechanism, which produces a stable inverted biomass pyramid. So one mechanism, which I'm going to show you, is well mixing. There's immigration, which this is what I call cheating. These two, well, this I'm going to show you. This is also in the book. And then the refuges, which I'm going to spend most of today on. So a short digression on the Lotka-Vatera predator-prey model. So this is the model. So V of t is the biomass of the prey. P of t is the biomass of the predator. Okay, think just great generality. Let me just try to explain what's going on here. So if there are no predators, if p is equal to 0, dv dt is equal to r times v. R is positive. So we assume that the food is unlimited for the predator, for the prey. Okay, this is, obviously it's okay if the prey population is not so large, but if it gets large, it's unreasonable, and then you can replace this with a logistic term, but this is the simplest term. Okay, if there's no, the predators only eat, the only food for the predators are the prey. So if there's no prey, dp dt is equal to minus qp, so the predators die at an exponential rate without food. An interesting question that I asked, and it seems like almost nobody has answered, only one guy has answered, is that really true? If you cut off so let's suppose that I have somebody lock the doors now. So you have no food. Okay, it's sort of the biomass or the numbers of people in the audience going to be decreasing at an exponential rate. And there are some plant experiments that say no. But anyway, this is the assumption. And then here, the prey are being eaten by the predators at a rate which is proportional to the product of their biomass. So again, this is well mixing. And again, what this means is if you double the number of prey, you double the number of predators, the rate at which the predators are being eaten doubles. So that means that they're sort of very intertangled. Okay, is this realistic? Well, maybe in some cases, yes. Certainly for the reef, coral reef, no. What this also implies is that alpha v is sort of how many, in some, I'm mixing up numbers with biomass, but that's okay. Alpha v is kind of how much food each predator eats at time t. So what this says is that, at some time, the predator eats this much food. But if there's twice as much food available, it's going to eat twice as much food. If there's 100 times as much food available, it's going to eat 100 times as much food. Okay, that's not very realistic. Okay, and the biological significance of these things, let me just leave for the book. So this is the model. Nonlinear ODEs, you can't write, there's no closed form solution. So what do? Well, first you find equilibrium points. There's an equilibrium point at 0, 0, and then there's an interior equilibrium point. So you write down the Jacobian matrix at those 2 equilibrium points, and this is it. So if you look at the equilibrium point at the origin, you look at the Jacobian matrix, one eigenvalue is positive, one eigenvalue is negative. It's a linear saddle. Hartman-Grobman tells us it's a nonlinear saddle. And then for the other equilibrium point, this is the Jacobian matrix. Its trace is 0. Its determinant is 0, is positive. Determinant is positive. So the eigenvalues are imaginary. Well, this is non-hyperbolic case, so Hartman-Grobman does not apply. So what do you do when Hartman-Grobman doesn't apply? Well, there's a conserved quantity. Okay, so if you take the ODE and you divide the top one by the bottom one, this is what you get. And this is a separable ODE, so you can rewrite it like this. So there are V's and dV's on the left-hand side and P's and dP's on the right-hand side. And then you can easily integrate both sides. And when you do that, you see that the quantity minus Q times the log of V plus beta V minus R log of P plus alpha P is a constant. It doesn't change in time. So that's the first integral. So this is a conserved system. It's also Hamiltonian if you change variables, but we don't need that. Okay, now it's known that for a so in general there are examples of differential equations, in fact it's easy to write down such examples, where you have a linear center, and for the nonlinear system you do not have a center. You have like an attracting spiral, repelling spiral or something like that, but not for a conservative system. So there's a theorem which says if you have a conservative system, then if you have a linear center, then that's a nonlinear center. And that's what we're going to use here. So what we conclude from this is that this is the phase plane. These are the orbits. All orbits are closed. So the solutions oscillate like this. And again, there's a long discussion about this in the book. Okay, so let's now go back to the well-mixed mechanism. So a more sophisticated version of this argument, we believe, will explain the inverted biomass pyramid for the phytoplankton and the zooplankton. Okay, I'm giving you the simplest version, but very much in this spirit, we think can explain the main example of an inverted biomass pyramid. So again, this is the system, predator-prey. Okay, I had to cut and paste some slides recently, so I'm sorry the constants are a little bit different. C represents the biomass conversion efficiency. So how efficient are the predators in converting what they eat into weight? Okay, so again, we did the calculation. 0, 0 is a saddle, but then we have an interior equilibrium point at the center. At equilibrium, what is the biomass ratio? Well, X of t is the biomass of the prey. Y of t is the biomass of the predators. You just divide the two. So this is the biomass ratio at equilibrium. And just looking here, it's equal to AC over D. So if this ratio is bigger than 1, meaning if A times C is bigger than D, or the exponential growth rate of the prey is bigger than the exponential decay rate of the, what am I saying? If the exponential growth rate times the biomass conversion efficiency is bigger than the death rate for the predators, then you have an inverted biomass pyramid. So if your prey turn over very often, and lots of population, very fast population growth, and your predators live a long time, and the biomass conversion efficiency is reasonably high, then you're going to have, and you have well mixing, then you have an inverted biomass pyramid. But obviously this is not the mechanism at pristine coral reefs. Okay, so now I need to talk a little bit about refuges. So as I said, in pristine coral reefs, the prey fish eat plankton and algae, and they hide from the predators in the holes, in the coral holes, and they try never to go out of those holes because those predators are very hungry. I should tell you, when they did this field study, they caught some of the sharks and they opened them up, and there was very little food in their stomachs. So the sharks are very hungry. Obviously, the amount of hiding space for the prey in the coral holes affects the amount of food available to the predators. Now, this might sound strange. In general, refuges can decrease, increase, or have no effect on the amount of food available to predators. If you think about that, that sounds ridiculous. I mean, the prey hide in the refuge, so there's less food available to the predators. So how can a refuge possibly help or provide more food to the predators? But if anyone has ever been to Jackson Hole, Wyoming, near Grand Tetons or Yellowstone National Park, there's what's called the National Elk Refuge. So just very briefly, there's tens of thousands of elk in Grand Teton Park in southern Yellowstone, and many of them would die, probably most of them would die over the winter from starvation. So the refuge feeds them alfalfa. So they know all to come down to the refuge, and it's a huge refuge, and they feed them alfalfa, and they survive during the winter. Well, the favorite food of bears and moose and wolves is elk. So because of that refuge, those top predators have much more food available to them. So anyway, we're doing experiments on this, and that's a different talk. But there have been very few experiments on how refuges affect predation response. Okay, so now what are the main open questions about coral reefs? So there's a nice paper by Knowlton and Jackson in PLOS Biology 2008 that sort of lists the main open questions. So one, what is the role of overfishing in degrading a pristine reef? Two, is it true that pristine reefs are more resistant to ecological shock than degraded reefs? So if an El Nino comes by and destroys or kills maybe 20% of the reef, will that reef grow back more quickly in a pristine reef than a non-pristine reef? And then some other questions. Let me just keep going. Okay. Also, this field study that I mentioned, if you look at Kingman, you look at Palmyra, you see that the coral cover, this white part of Kingman, is more than twice as large as the coral cover of Palmyra. And you see up here that this is the amount of top predators, and this is the amount of, you have to add up plantivores and herbivores to get the prey, but you see that there's a much larger inverted biomass ratio for Kingman than there is for Palmyra. So there's speculation, again, just using two data points, that the larger the reef, the more inverted the biomass ratio. And the question is this true? Is this a general fact? Okay, so let me report on the first stage of our research project. So I'd like to think that we just entered stage 2. So what we do is we write down an ODE model, which I'm going to show you, of the fish biomass in a pristine coral reef. And our model exhibits a stable inverted biomass pyramid when we add what are the most realistic parameters we can write down. As I'll mention, a couple of these parameters are just guesses, but they're the most biologically reasonable guesses. A key component in our model is a refuge. Now, people have modeled with refuges before, but not with an explicit size, because we want to show the dependence of the biomass ratio on the size of the reef. So we needed to add to include explicit size. Our model is as faithful as we could be to the recent field study and to other observations. And indeed, our model shows increasing biomass ratio with increasing refuge size. increasing coral size. And then at the end of the talk, I'll show you, we study the effect of fishing in the model. So our model has one predator class and one prey class. Why is that? That might seem a little bit primitive. Well, it's not so primitive because the field study and other investigators observed little direct competition between the different predator species and the different prey species. So there's not much interaction between them. It's a little bit surprising, but they seem to be pretty certain about that. And in part, the biomass data is only provided for the combined predator class. And again, we want to be faithful as we can to the study. We assume that the prey biomass grows. Exponential was just too primitive logistically. Okay, and this is, you can read about this at the beginning of the notes, and we assume that predators die at a relatively slow, constant rate D. R is the refuge size, and this is the functional form of the model. Okay, so this is logistic growth of the prey, but this is a little bit strange. Well, this is maybe very strange. This is the prey growth rate is a function of the refuge size. So this is the type of thing I wouldn't dream about if I wasn't working with a good biologist. And of course, I'll explain this in a minute. What is f of xr? This is what's called the predation response to the predation function. So basically, let me not be completely precise, but let me give you the idea. And that is, B is the maximum predation rate. F of xy is basically how much biomass each predator is consuming per unit time when the prey population is at x, the prey biomass population is at x, and the refuge has size r. Okay, so if you think about this, if r is large and x is small, that means that almost all the prey are hiding in the refuge. So they're inaccessible to the predators. So the predators are going to be eating almost nothing. So if x is much less than r, this term is going to be very close to 0. That means this interaction term is going to be very close to 0. That make sense? And then if there's a huge amount of prey and a small refuge, then the refuge isn't going to help very much. Is that okay? This is an absolutely key fact. Okay. And then for, again, here for the growth of the predators, the only food available to them is the prey. So they're consuming them at this rate, right? The same here up to this constant. And then this is the death rate, the natural death rate. Okay, so the predation response function, and again, just one more time. You think that this is for each predator, how much prey it's going to eat per unit time if the prey biomass at the time is x and the refuge has size r. And we assume a function of this form. Okay, so again, if the we fix an r, so here we're fixing an r. If x is much less than r, then all of the prey can hide in the refuge. And none of them are available for the predators to eat. That's why the function's almost 0 here, right? And then it starts increasing as the number of prey starts approaching the size of the refuge. And then after a while, you know, again, if we go to a churrascaria, you can only eat so much, right? It doesn't matter if they keep bringing more and more and more food. You can only eat so much. That's why this curve approaches as an asymptote. Now, we choose a particular functional form. Biologists can't give us any information. They don't have any measurements. They don't have any experiments on this. So what we do is we choose a functional form, and then we choose another functional form, and then we choose another functional form, and then we try to hope that our conclusions are robust with respect to the functional forms. That's the best we can do. Okay, and then why is the exponential growth rate of the number of prey when the prey population is small? That's essentially what A is. Why is this a function of R, of refuge size? Well, and again, this is something which we would never, as mathematicians, we would never ever know without working with biologists. So several studies, including some fairly recent studies, show that refuges in coral reefs help the survival of very small prey, and that an increase in the refuge size can increase the prey growth rate. So they've done some experiments with this, some field studies experiments with this. So indeed, it looks like A is a function of R. Obviously the coral holes protect the very small fish. So again, the exponential growth rate for small prey populations is a function of R. This is what the biologists tell us they think it should be. Again, there are no real measurements. So why this particular function, I can't tell you. But the biologists tell us that they believe that, for the reefs we're studying, that A of R looks something like this, with these numbers, by the way. These are their best estimates for numbers. And again, what we do is we use this particular function, and then we try another function, that has a graph like this, and we try to show robustness, that our conclusions don't depend very much on the function. So this is the functional form. I told you what F is. I told you what A is, A of R is. This is the actual model when you plug in numbers. I did. So this is more or less F, 1 over 1 plus e to the minus 10x minus r. So it's a system of two ODEs. It's not exactly what you see in textbooks, but you all know how to analyze it. And K is the K is the carrying capacity, the natural carrying capacity for the prey if there are no predators. And this is difficult. This is the biggest guess. Because, what if you remove all the prey? If you remove all the predators, will the prey come out of the holes? Well, somehow they're adapted to living in the holes. So if you want to publish a paper in a biology journal, and we very much want this to appear in a top journal, actually in coral reefs, you need to argue these things. Okay, so we chose something in the middle. So we assume that K, well, let me not get into that. D, like 0.005 per day, where does that come from? Well, that comes from the fact that reef sharks and other reefs, so let me back up. This reef has only been studied for about a year. Reef sharks live at other reefs for 25 years. So obviously there haven't been long-term studies at this reef. It could be that predators at natural reefs live longer lives or much shorter lives than they do at conventional reefs. But there's no study to tell us how long these sharks are going to live at this particular reef. So we have to use data that they live. Gray reef sharks live about 25 years in other reefs. Okay, if anyone wants to know about any of these other constants, just, what is B? So B is the maximal predation rate, and that corresponds to, again, for reef sharks at other reefs, 12% predator body mass per day. Imagine that, eating 12% of your body mass every day. Okay, so this is the model. Let me go back, sorry. What do? Find equilibrium points, determine their stability, study bifurcations. So there are 3 equilibrium points, 0, 0, at K0. So that means that there are 0 predators, and the prey population is at its carrying capacity. Not going to happen, so obviously the first 2 are non-biological. And then there's an interior equilibrium point. It's locally attracting, and this is it. You can write it down kind of explicitly. So what does this mean? That means that this is at equilibrium. This is the prey population in a reef of size R. And this is the predator population in a reef of size R. So what's the biomass ratio at equilibrium? Well, you just divide the 2. It's this divided by this. And that's all we do here. So this is an explicit form. Well, just to simplify it, we wrote it as A of R, but we have an explicit form for A of R. So the point is that we have just a formula for the biomass ratio. I mean, it could have been so bad that, we couldn't write this, we couldn't write this. Obviously, we couldn't write this, but it turns out to be kind of simple. So what we did was we graphed, sorry, let's go back. So with the parameters that we chose, we graphed this function as a function of R. And this is what we got. So this is refuge size, and this is the biomass ratio. The predator biomass divided by the prey biomass of equilibrium. And you see that it starts at 2.2, so it's inverted, and it goes up to 4. And it's almost linear, which is surprising. We can't explain this, but it's almost linear. And you see clearly the larger the refuge size, the more inverted the biomass pyramid, the biomass ratio. Okay, so our model gives the inverted biomass pyramid. It gives the increasing dependence of the biomass ratio on the reef size. And also, if A of R is constant, then we obtain an inverted biomass pyramid, but we don't get the dependence. Okay, so now just a few minutes about fishing. So this is the original model. And now I'm going to add an arbitrary prey fishing term, which I think is a little bit silly biologically, but it's here. Because the reason it's silly is how are you going to catch the prey if they're hiding in the coral? Okay, but there's an implication here which is kind of interesting, so that's why I keep it. So this is prey fishing, and then we assume so-called proportional fishing or constant rate fishing, that the predator fishing decreases the growth rate by a rate proportional to the biomass. So this is a pretty standard assumption. And if you look at the new biomass ratio, you get a formula. And this piece is what was on the previous slide. So this is the biomass ratio without the fishing, and this is the fishing term. But it's minus something which is positive regardless of P. So this little calculation proves that regardless of the prey fishing, how you fish for the prey, the biomass ratio decreases. Which makes sense, but this is a proof. Okay, now what we do is the green, we fix a moderate level of predator fishing, which is this amount. Okay, and then you have 3 curves here. The green curve corresponds to no prey fishing. The blue curve corresponds to a little prey fishing, And the red curve corresponds to, let's say, a lot of prey fishing. So if there's no prey fishing, just predator fishing, look what happens here. So if the refuge size is between 0.6 and, I don't know, 0.8, we lost our inverted biomass pyramid. Because these numbers, this ratio is no longer bigger than 1, it's less than 1. So this shows very clearly in our model that just predator fishing can change the inverted biomass pyramid to make it a normal biomass pyramid. And then it's much worse when you, or it's worse, maybe much worse, when you have prey fishing. So one of the big questions is why is an inverted biomass pyramid a signature of a pristine or natural reef? Our answer is because in a pristine or natural reef, there's no fishing. And then if you have fishing, then that would destroy the inverted biomass ratio. Okay, so the conclusions are that the inverted biomass pyramid we think is a consequence of little or no fishing. And if an inverted biomass ratio is indeed desirable, if it is indeed a signature of a pristine reef, then you want to reduce all fishing. And also, this is, again, I wouldn't present this to biologists, but if an inverted biomass ratio is desirable, then do what you can to enlarge the reef. And our current work is to add coral growth to the model. So up until now, the coral has been static. But coral grows, it dies. El Nino typically, which I think is happening now, frequently kills a fairly substantial percentage of the coral. So there's interesting dynamics to the coral. So we want to add coral growth to the model. One of the big biological problems here is, are predators and prey good for the coral or bad for the coral? And that's not so well understood biologically. But we're hoping that we can understand some sort of crude questions. Okay, that's it. Thank you all for your attention. Any questions?